The title of this presentation is What are phase diagrams and are they important? The presentation is the introduction of phase diagram section in the course High Temperature Materials. In this lecture, I'll try to introduce the concept of phase diagrams and communicate why they are important by giving two examples from actual metallurgical processes. Why do I start at this end? Well, when learning phase diagrams, it is common to study hypothetical systems of components A, B, and or C. While this is an effective way to learn how phase diagrams are structured and used, it might be lost how they are applied in reality. And if we don't know why they are important, we have less motivation to learn this fundamental tool. The knowledge of how to utilize phase diagram is fundamental as an engineer in metallurgy. In fact, they might very well be one of the most useful tools you'll encounter in your degree program. Phase diagrams are applicable to alloys, slags, and refractories used in furnaces. Naturally, other fields also utilize phase diagrams as well. They can be applied in glass, ceramics, and other high-temperature technologies. I'll introduce two applications later, but first, let's define what a phase diagram is. A phase diagram is simply a graphical representation of equilibrium states of a system under different temperatures, different pressures, and different composition. But what does it mean? This is a simple case that will be covered in the next lecture, that is, the one-component system. Surely you have already seen this diagram for H2O if you have studied introductory courses in physical chemistry. In the figure presented here, you can see the different aggregation states exists in equilibrium under different temperatures and pressures. However, there is just one composition in the diagram since the system consists of one component. We will not go into more detail as of right now. Instead, we will add another component forming a two-component phase diagram. This diagram is a bit more complicated, but you'll learn all about them in the third presentation. Let's focus on these three parameters affecting the equilibrium states. You can clearly see the changes in the phases occur as we move along the temperature y-axis. You may also see that different compositions along x-axis changes the phases that are in equilibrium at a constant temperature. Differences in pressure is not accounted for. This diagram represents the equilibrium at a fixed pressure. If we add one additional component, arriving at 3, the phase diagram can appear intimidating. However, when we progressively add one component at a time during this course, you'll find that they are quite welcoming to use. You can also suspect that there are some seemingly hidden information in the diagram, as we should have 5 variables but operate in the two-dimensional field of this PowerPoint presentation. The variables, these 5 variables, are component A, component B, component C, temperature, and pressure. A diagram with 5 variables is quite hard to demonstrate in space as we know it. In these 3 component diagrams, we have compressed 4 variables, the pressure being constant, to the two-dimensional space of the PowerPoint slide. The compositions can be read on the 3 axes given here, and the temperature are actually drawn as isotherms in the figure. Before we move into the next lecture with the one component diagram, we'll have a look into why these diagrams are important. So, are phase diagrams important? Understanding phase diagrams is useful in many applications. In this introduction, I'll give 2 different examples to illustrate this, one regarding refractories and one regarding refinement. As we have not yet covered how phase diagrams are constructed, many details can be hard to grasp in these examples. However, they're still useful in placing the upcoming lectures in a bigger perspective, which gives a motivation as to why you should learn these phase diagrams for your future career as an engineer. I encourage you to go back to these examples later when you have gone through the future lectures. The first example that we'll cover is the refining of lead. Silver is commonly found together with lead, and in the lead production, you have to remove the silver. How do you do this? Well, a first step is that we look into some phase diagrams. We start off by the binary AGPB, that is silver lead binary phase diagram. A few notes on the diagram. Down here on the x-axis, you have the mole fraction of lead. This means that here you have 100% silver and here you have 100% lead. On the y-axis, the temperature is represented. The uppermost area of the figure shows the liquid phase, and you can think of this as mixing of ethanol and water, but here you mix lead and silver forming one liquid. In the lead making, we will be somewhere here in the system because we have mostly lead in our melt. And you can see from the phase diagram that the liquid is not solidifying until somewhere around 300 degrees Celsius. And you can also see that there appears to be no way to remove the silver from the lead. Therefore, we'll consult some other phase diagrams, namely the silver zinc and lead zinc binary phase diagrams. So in this first one, the silver zinc, you can see at the higher temperatures, we have that the metals form one liquid phase, and if you cool it, they will form some intermetallic compounds. As far as the zinc-lead system is concerned, above 417 degrees Celsius, you can see that we have two liquid phases, which means that lead and zinc are immiscible. You can think of it like mixing water and oil. In this case, lead is the heavier phase, and it will be placed in the bottom of whatever crucible or ladle you have. If we consider these two binary phase diagrams together, we can actually determine that at higher temperatures, we can facilitate a higher solution of silver into the zinc phase. The liquid zinc phase can then be separated from the liquid lead phase, and in this way you can remove the silver from the lead via the zinc phase. If we then cool the system, the intermetallic compounds here formed by silver and zinc can be removed as they crystallize as a solid phase before anything else. So this is a refining principle that is employed in industrial lead production. And as I said, I encourage you to return to this example after you've gone through more material. The second example concerns the refractory in basic oxygen steelmaking. Refractory materials are necessary to use in metallurgical processes operating on high temperatures. In basic oxygen steelmaking, the temperature increases during the oxidation of silicon and carbon and reaches a final temperature in the range of 1700 degrees Celsius. Therefore, the inside of the converter is lined with refractory material. The figure illustrates an outline of the converter with the working lining and the safety lining marked. The lining used in the BOF converter range from pitch-bonded magnesia or dolomitic types to the advanced refractories that are made with resin bonds, metallics, graphites, and sintered and or fused magnesia that can even be 99% pure. These refractory bricks are designed with a combination of critical physical properties to withstand the high temperatures and rapid changing conditions throughout the blowing cycle of the BOF. Naturally, poor properties would mean more frequent relinings of the converter, which is accompanied by cost. A balance of properties such as hot strength, oxidation resistance, and slag resistance are necessary for good performance and long lining life. In this example, we'll consider the slag-resistant aspect in terms of slag design. Assume that we have magnesia brick, which is MgO. The BOF slag composition varies during oxygen blowing, but the major components are CaO, SiO2, FeO, and MgO. One of the desired outcomes of the process is to lower the sulfur and phosphorus content in the melt. The refining capacity of sulfur and phosphorus is greater for CaO than for MgO. So we ask ourselves, do we really need MgO in the slag if the refining capacity is worse? Well, the fact is yes. And why? We have to take a look at the phase diagram. One function of MgO in the slag is protection of the lining. If we don't add MgO in the slag formers, the slag will dissolve MgO from the refractory lining. Thus, by adding MgO, you can minimize the refractory wear and extend the campaign life of the converter before relining. Based on the phase diagram, we can understand why an MgO-saturated slag will minimize the dissolution of refractory MgO in the slag phase. How do you do this? Assume your three main slag components can be reduced to CaO, SiO2, and MgO. First, the slag composition in the BOF slag is quite basic with a basicity of B2 around 4, so it's somewhere around here. Now, a basic slag is less determined to dissolve MgO than an acidic slag, but you should still be within the primary crystallization field of MgO in order to minimize the MgO dissolved from the refractories. Now, the primary crystallization field of MgO is this field. And why is this the case? If you have a slag composition within this primary crystallization field of MgO, the first crystals to precipitate upon cooling of the slag is MgO, or at a given temperature, there's a certain composition of MgO that saturates the slag before additional MgO is not dissolved. So if you're at this position by your slag formers, you'll prevent refractory MgO from entering the melt. Now, if you didn't understand these examples fully, that's completely fine. Please note, however, that these applications are very real, and without understanding phase diagrams, they are hard to grasp. With that being said, we conclude this introductory presentation and move on to the simplest phase diagram, that is, the one-component system. Thank you for listening.